Okay, so welcome everyone to the first talk of the Mathematics of Motion seminar in the semester. Today we will have Teddy Lazebnik from the University College of London who will talk about SciMED. So Teddy, you can begin.
Hi, thanks. Can you allow me to share my screen? I think it's blocked.
Yes, you can share it now.
Great, thanks. Cool. So hi everyone again. I will try, since I'm the first lecturer in the series, I'll try to be quick and make it like in less time than usual. More than that, for this presentation, I decided to move out from the classical PowerPoint and try to go with you over the paper itself. So it's maybe a bit unusual for both of us, but let's give it a try. I believe that in the paper we have a lot of technical details that can be interesting for this audience and everybody that will see the recording afterwards. So first of all, I would like to thank Liron Simone, which is here today, I guess, and Professor Alex Liberzon. They are the co-authors of this paper, and I must say Liron is the one led the way most of the time. So thanks for them. And without further ado, SciMED. So the idea, or let me start quickly by a motivation. So it's not unusual that we get in a lot of data from experiments, and from the experimental data, we want to capture a more generalized theory of some kind of dynamics. It can be from physics, it can be from like biology, etc. Let me give you an example. Let's say you have two species that are interacting in some manner. You sample a lot of features about the interaction of the species, and you try to understand if there are some the global dynamics. For example, the classical mathematical prey-predator dynamics. So we know that have two differential equations that describing the population sizes of the prey and predator. So if we can actually, from a simple observation, extract these more or less generalized ideas. So this task actually not left unnoticed by other scientists. And in general, we call this task a symbolic regression. The idea is that we'll be able to represent the empirical data using symbolic functions and not, for example, machine learning against other sophisticated tools that's actually providing us a generalized but numerical solution. So symbolic regression is really, really interesting. Unfortunately, it's written somewhere here, as you can see. A recent paper actually showing first time, actually really, really recent from 2022, showing that symbolic regression in its more generalized form is NP-hard, which we all know is a bad thing to have, or a good one if you're a computer science and need to publish papers. But in general, we don't like NP-hard stuff, which is unfortunate because we don't able to just run through all the possible hypotheses and get like a decent solution from the data. By the way, there are approaches actually saying let's brute force our way, but they're failing really quickly from several reasons. I think the main one is when you take in a data which noise and you brute force your way through all the possible solutions, you really quickly get in an overfitting because you try to get a polynomial or some kind of higher order function to capture the noise itself and not the more generalizable data. So the audience probably comment with this kind of problem from machine learning and classical tasks, so like fitting. So this is actually really, really hard. So there are a lot of ways to do symbolic regression. Let's focus on four main groups. So there are a lot of ways, but we can actually divide it into the following four groups. The first one is, let me jump over. So you can see the first one is brute force solutions. So again, basically, it's not really brute force because it's really hard to organize how hypothesis looks like for symbolic regression. But let us assume we have some basic arithmetics and functions, and constant and whatever else you want, and we can actually construct or we have a construction rules for these functions. It can be as simple as you get in two functions of two constants and we have a function between them, but it can be as complex as providing any sub-problem on top of the argument. So both ways are acceptable. Actually, respectively will be in 37 and 39. And you actually brute force all the possible construction combinations, sometimes stochastically, sometimes deterministically. It's either way, it's not a good idea. So brute force is a nice like start, a naive start, so you can get a solution, but it's more often than not just not feasible for real case and real data. A more recent approach led by the Cindy paper is the sparse regression systems. So imagine yourself the following question. If you want to represent a model, you want to be as explainable as possible. Namely, if we focus only for a linear system for a second, you can present a linear system using a matrix, right? So what kind of matrix will be more explainable? A matrix with more zeros in it, because you have less terms shown around in less equations. So the system is actually smaller as much as more zeros are appearing in the matrix describing it. So if so, a really, really sparse matrix is a really good one. So basically what we want to do is we want to find the most sparse representation of a family of functions, a given family of functions that's representing the dynamics and fit in the data. So you have like two powers over here. One power trying to, or two forces. One force try to minimize the number of terms that are not zero in the matrix representing a system. And the second force is trying to include more terms to represent, to fit better the data. So when you're optimizing the two forces, you should be getting some decent result in between. And Cindy actually showing a really promising outpost right now. It's considered not current state of the art, but almost the state of the art. So this is the second approach. Deep learning, and I don't like it, but everybody needs to use deep learning nowadays. So deep learning is great, it just works. We don't know anything basically why it works or how it works. It just, as usual, just running through a lot of possible combinations some way and generalizing the way we find symbolic regressions. I don't think there's much to say. Even in the papers themselves are proposing symbolic regression using deep learning. More or less declaring is an engineering problem, saying we don't know why it's working, but check it out, it's worked really well. So we'll skip it now. And the current state of the art, at least according to recent benchmark papers, is the genetic algorithm-based symbolic regression. If you're not familiar with genetic algorithms, let me quickly review it with you. So most of you are probably familiar with the idea of evolution. So you have a species, or a lot of species, and you have a population inside the species at any given time. So the population has individuals who are more fitted to live in the world, and some individuals are less fitted to live in the world. So the less fitted will be eaten, will be, I don't know, jumping from a bridge or any other bad idea, and will die out, and the more fitted will be, like stochastically will live and prosper and have children. So the children will continue to contain the same genes or some properties that allow their ancestries to live and provide them the ability to be born. So you have this like natural selection. And if you repeat it enough time with some kind of like mutation magic and other properties that I will skip for a moment, you will eventually converge to really, really promising species, which is, look at nature, they're really good stuff. Like they can fly, they can be underwater, so they have really super cool superpowers, which you need to mutate for a few generations to get this kind of cool capabilities. So this is the basic idea. And again, if you look on this on individuals or populations, not of species or animals, but of solutions for a problem, you can actually adopt the idea of evolution, to how we search for a problem. So it's basically a heuristic search inside the possible space. And actually, genetic algorithms are used all over the place, and in symbolic regression as well. and currently considered the state of the art, as I stated before. In this paper, we compared ourselves to AI Feynman. AI Feynman is an AI system combining, I will say, like sparse regression with deep learning. It's more complicated than that, but for now, let's assume it's like a strange combination of the two of them, and actually contributing 4, or at least the authors claims to contribute 4 different ideas to the symbolic regression domain. So they're currently considered the state of the art by many. A really interesting paper published in Science in 2020. So I really recommend you to at least quickly read it. And I think that's it. So there are more details over here. If you want, you can read the paper afterwards. Any questions up to this point? Okay, so I'll continue on. So this is like a really quick introduction to the domain. And now you may ask yourself, okay, it sounds really dense here. So a lot of different solutions grouped into groups. What do you provide to the table? And this is a really good question. Thank you for asking. So the answer is that we actually looked about how the systems work, and we noticed that as a domain expert, not me, I'm not a domain expert, but Liron, for example, she has a lot of experience with physics, and she wants to solve a physics problem. And she asking, okay, so I want to provide a computer my knowledge, but it's not really easy. So how can I provide my knowledge? So some will say, okay, adopt somehow the loss function, but the somehow it's always a mystery, and you need to solve it for each case independently. So can we find some idea of some mechanism that will allow us to introduce domain knowledge into the system without the need to adaptively do it for each problem by itself? So this is the motivation, and the answer is yes. So we propose a scientific machine equation detector. So the equation detector just sounds better than a symbolic regression, but it's more or less the same. And scientific machine is because we want to actually combine how we as humans solve this kind of problems, the reverse engineering from data to a theory, and how the computational approach of symbolic regression doing the same task. So if we can combine both capabilities, we believe to obtain better results, which actually I will show you in a second. So I think the following the following figure will shed more lights about how we plan to do it. So first of all, it all starts with the data as usual. So we have like source parameters, and we have a target parameter or feature if you're a computer scientist. So we have the data and we have the system. So the system, or SciMED for short, combines 4 already well-known components. The first one is feature selection. Basically, we are doing the following stuff. So feature selection, it's a domain by itself. It's an interesting topic. It can be spent hours only discussing how to perform feature selection well. But for now, let us assume that feature selection is done and currently done by a genetic algorithm. So basically, we have a list of features that we can take from, and we have a subset that we allow to take. And we're actually building a population of possible reductions. Namely, if you have 100 features and you want to take a subset of size 10, for example, you have a gene which indicates in what 10 features we took from the 100 features, and we have a lot of possible, like 10 of 100. So we have a lot of different genes all around the population. You run in the genetic algorithm, and hopefully, there are no promise it will happen, but hopefully you actually converge to some optimum in what kind of features will be fine. You may ask, and you will be right to, how do you measure a goodness of feature selection? So we're using a method called a wrapper feature selection, which basically we're using a feature selection, and we're using an algorithm, a learning algorithm beneath it, and we're making like a loop with both of them. So you actually don't measure the feature selection itself, you're measuring the performance of the overall pipeline, feature selection plus a machine learning algorithm. Okay. Now the following question will be, okay, but the feature selection algorithm, the feature selection is heavily dependent on the learning algorithm that they choose, because a result from decision tree, it's not the same result for, I don't know, SVM or even random forest, or just name it. So you can say it's actually really dependent. And picking and different feature sets can actually be better adapted to different algorithms, which is all true. And therefore, we are using, as you can see here, an AutoML exploration. So basically, we don't choose in only the feature selection, we're choosing the feature selection and the adapted machine learning model and the hyperparameter tuning in the same time, doing it over and over again. Cool. For the technical details, the AutoML, and we didn't implement the AutoML, we thought about it, but decided to adopt the Teapot AutoML library. So if you're not familiar with the Teapot library is again using a genetic algorithm, a different kind this time. So we actually, you can think about it as a two-phase genetic algorithm. We have a large population of feature selections and algorithm selection in between, and the second population for each one of the candidates from the first one of possible models and their hyperparameters. So you're basically searching for two particular space searches, one for the feature selection and one for the model and the hyperparameters. Any questions up to this point? Okay, so now what you get from this process is you can understand what the features and their importance. This is a classical after you obtain the model and everything. But the question is, how do you introduce the domain knowledge to the problem? So basically, you can say, okay, I have a lot of features, but I know something about the features. For example, I know that if I choose A and C, if I choose A, I must choose C. Or if I have some kind of a relationship or condition that the features must obey to, I can introduce it as a function to the first search space. So all of this actually can be introduced really easily just using one function in the code as part of the searching algorithm. So this is called the feasibility operator in the function. So if the feature selection set it's not satisfying the feasibility operator, it just doesn't run, and you're actually punishing the model. You're given like -infinity score for trying to go to this like far black zone, and you by doing so, you actually constrain it to a desired domain, which is governed by the domain knowledge that you introduce to the system. And so you can actually, by introducing the right domain knowledge, reduce significantly the space, obtaining a better results and faster results. Next, once we have the features and we have, so I actually skip, but we can enrich the domain of data, etc., etc. It's really important for physics related tasks, because in physics you actually might have throughout, because let me gather my ideas again. In physics, when you do experiments, you can be sampling not equally distributed the domains that you're interested in. So you might want to enrich the data to the entire domain, or better than you sampled, in order to get a more like equally distributed sampling set, which will be better used for the next component. So this is an important point in by itself, but a smaller one. Next, we have two different symbolic regression, classical symbolic regression components. The first one is genetic algorithm. Again, we adopted something already known, and we played with like with the ideas of it. Here, you can actually introduce two more domain knowledge. The first one is the loss function. So we make the loss function really, really easy to adapt in the manner of we allow you to pick what properties the solution should be. You can actually adapt to a simpler solution in the cost of less like performance or less fit and accuracy, where you can ask for a faster solution, etc., only by checking a box. And feature weight is you can say, okay, I can look not on the entire search space, but I can think about subset of the search space and be really, really good, like get a really good fit on this subset in the price of another subset. So usually it's really important when you have some kind of parameter that you really, really not want to miss in any way. The result of the GA-based symbolic regression is an equation, as I described before. And the next component is similar, is the Las Vegas symbolic regression, which is a stochastic version of the brute force. again, in this time, in order to reduce the space size, because it's exponentially large, you can govern the equation structure. For example, if you have an hypothesis that your features has like a formula of A, like in the power of B plus C in the power of D, etc., you have some structure. You don't need to check all possible polynomial combinations of a function. You can actually just try out a really specific structure. And we're making this structure really easy to obtain using it's really easy to obtain computationally using a binary trees. So it can actually describe below. And data sampling strategy, again, we can actually govern the way we look on the search space and provide more, for example, computational powers to places we hypothesize are more promising and less computational time to the domain of the space. So we actually can govern the computational time and powers that we provide to the Las Vegas to provide a better solution. Any questions up to this point? I think it's enough. Okay. So here you can see a lot of math, which actually describing everything I told you in the last 10 minutes. I really encourage you to read it out because it has all the details that I missed. Cool. So now you may ask yourself, cool, Teddy, it sounds promising, but how do I know this is actually working, or is it working at all? And the answer is yes. Otherwise, we didn't have the paper. But let me show you why the answer is yes. So first, we tried, because the domain is which is interesting for us is physics. We try to solve physical problems, which is a nice exercise by itself. So we're actually interested in 4 problems. The first one is you have a ball in metal air. They don't have any drag. You're assuming it's vacuum something, or not something, it's a vacuum. Just dropping the ball from the air, and you're asking what is his height in some specific time. So you have the original velocity. You have the acceleration, x2, and you have the time that's passed so far, so x3. I know that because I'm simulating the data, but the computer doesn't know it. It just has 3 parameters, x1, x2, x3, and the computer needs to find out this is the right equation. Again, notice that it doesn't take into consideration any physical knowledge at this point. Afterwards, we make the same experiment, but this time with 33 features. As you can see, we have 30 and 31 only in the answer. So here in the second experiment, we actually focused on the model's ability to make the right feature selection, because you have 36 parameters which somehow correlated to each other, have a lot of possibility to mess up, and picking the right A constant B features, it's not trivial at all. Then we go to the same problem, but this time with drag of air. So you have a nonlinear system, as you can see over here. This equation is still considered relatively simple because it's polynomial and everything, but it's not trivial anymore. Specifically, I want you to notice that we have, again, a really interesting constant. I'm not the right guy to tell you why 13.808 is the right number. It's not a single constant in the system. It's actually a computation of several physical constants, which shown in the data as a single number. So the ability of the model to actually reconstruct the physical process that's generating this magic number, it's not trivial as well. Finally, in the last experiment, as you can see, we actually dropped 0.4 from the same experiment, which shown here in the second order, and asking the model, okay, can you find an answer? And the right answer is you shouldn't be able to find it. So if you find it, it's really, really bad. Let me explain why. Imagine that we don't know the answer and the computer finds an answer. Okay. We might think this is the right answer, that's actually generalize our data and use it further in the process. And this is a big no, because we don't want to use an inappropriate function to describe our data. We want the model to be able to alert us and say, check out, we have a problem. So the first experiment try to see if this feature actually works for SciMED. And as you can imagine, the answer is yes. So first of all, we're looking on our two-level genetic algorithm feature selection for plus AutoML pipeline. So the first two components, if you may. So you can see the performance of experiment A is almost perfect. Experiment B is almost perfect. It's not surprising. It's really linear function, which shouldn't be that hard for numerical simulation nowadays. Experiment C is not linear, and you can see a small drop in performance, still almost perfect. And experiment D is obtaining a similar result. This is actually really annoying because hypothetically we want to find something that's saying, okay, this shouldn't work. But it's for our amuse, was able to find a higher order connection between Z1 to Z2 and Z3 with Z4, which we dropped, as you recall, and therefore was able to capture actually decent result. Not the desired outcome, but an interesting outcome nevertheless. The next point was, okay, so the numerical process is great. Can you find the symbolic regression function? And the answer is again, yes. So if we take in the AutoML pipeline performance and then run in the two other components, you can see that while the GA and Las Vegas symbolic regression obtaining a less accurate representation due to the noise, you're actually obtaining a decent one. And more importantly, the R square and the t-test p-value, this is almost a one, which saying they're not statistically different. Notice that it should be small to be statistically different. If it's close to one, it's actually good for us. And the R square is almost one, saying that even if we have some error, do some like background noise, we actually explain the data almost perfectly, which is exactly what we want to. And the last point, which I find the most interesting one, or the last two, which really interesting, for the experiment B, okay, so the GA symbolic regression actually wasn't able to obtain like the desired result, while the Las Vegas one and the AutoML is actually was able to do so. And more importantly, if you're checking out experiment D, so again, C is not linear, so this is actually interesting. And more importantly, in D, when we checking out again the AutoML, we get in the same result as before, the annoying but good one. But the symbolic regression actually alerting us, more importantly, that the p-value is not high enough, and indicating for the user, which is actually really easy, if p-value is small enough, just make an alert saying there's something wrong going on. So this is actually alerting to the user that something is bad happening and you should do something about it, which is exactly what we want to obtain. Okay, any question up to this point? Okay, cool. So I'm almost done, bear with me. So this is the results from SciMED compared to the AI Feynman. You know, every time that you're making a paper about computer science engineering, you need to show that you're beating the last smartest guy. So this is not any different. So AI Feynman was able to obtain the first linear function. This is not a surprise. It's able to obtain the second equation, again linear, but AI Feynman, throughout technical issues, is not able to find the constant, which is great for us. Again, it's performing really, really well on the third equation. We are performing even better. Please recall that the right constant is 13.08. So we really, really close. Here they are around 50% error. So the 004 over here is an error, our error, but it's relatively small. So I hope you find it fine. And D, we actually obtain a result, which is not really good because it shouldn't be like that. But when we run this result, which the data we actually can show that the result, again, obtaining a really bad performance, and we can alert the user. So we can say, this is my result, but I think it's wrong, which is great. And AFM1 wasn't able to, excuse me, obtain a singular result because it continues to try by design until it's converged enough, but it seems it didn't converge enough to the time that we provided it to compute it, and it's raising in over 50 times. I think everybody in the audience will agree that 50 times is not explainable if the model should be like 5-6 terms length. So this is an obvious failure. So we are beating the biggest guy, but in nature, as a last comment, you never get a simulating result. You never get like the pure, I multiply two numbers, getting the right number and everything. You always have like an error to measure stuff. You have an error in storing stuff. You have just too many errors all over the place. And unfortunately, you have errors in both the like features, the source features, the target feature, and usually you have errors in both. So we may ask how well we're performing on like both experiments. So we have experiment A, which I recall is the linear one, the easy. Experiment C is the non-linear one, the hard one. And we have the two components. We have the GASR, which is relatively fast and computationally not expensive. And the Las Vegas one, which can be really expensive really quick. So our answer is, if you increase the noise in either the source, the target, and both, how well we still performing, or if you want, the success of outcomes. Again, notice the GA and the Las Vegas are both stochastic, so we want it to success most of the time. As you can see, in experiment C, it's dropped really quickly. Note on the yellow line. And on the A experiment, it's actually quite stable. Okay, so you can see in the 50 line, which is actually marked here, this is more or less the place we're feeling comfortable with, because you need majority of times to pick the right outcome. So even 3% in linear functions, 3% in the input and the output is still fine for us, but even 4% over here for the Las Vegas, which is much more computationally expensive, 5% is like the limit. And relatively, 3 and 5% is not much. So while it's promising, because if you put this kind of data inside other models, for example, AI Feynman, it will collapse relatively quickly. So we actually obtain better results, but it's still not enough to be feasible for real data, which like 10, 15, even 20% of error from time to time. So this is actually really important future work. And that's it. And you have a lot of details if you want, too much if you ask me. Cool. Any questions?
Okay, so if there are no questions, let's all thank Teddy. It was a very interesting talk. So thanks very much for giving it. So.
Yeah, you're really welcome.
Okay, so I guess we'll meet everyone next week in the next talk. So see you all. Bye-bye.